All right, so the final talk is heuristic algorithm for solving restricted SVP and its application by Geng Wang, Wenwen Xia, and Dao Gu. And the talk is recorded, and the speaker is Geng Wang.
Good morning, everyone. The title of this paper is Heuristic Algorithm for Solving Restricted SVP and its Applications. My name is Geng Wang from Shanghai Jiao Tong University, and this is a joint work with Wenwen Xia and Dao Gu. I'm sorry I'm not able to attend the conference in person. This work is mainly about lattice-based cryptography, and since a quantum computer poses great threat to the classical public key crypto systems like RSA and ECC, lattice-based cryptography becomes the most promising candidate for a post-quantum world. And in the NIST post-quantum centralization process, two lattice-based algorithms are selected as the recommended standards, including Kyber and DILISM. DILISM is the digital signature algorithm. The basic lattice hard problem is the shortest vector problem SVP, which aims to find a length of shortest non-zero vector in a lattice, and the length is denoted by lambda 1 L. L is the lattice, but the value is usually unknown. So to solve this problem, we can use Gaussian heuristic for a nice approximation to lambda 1. And the following algorithm finds a short vector lattice vector V according to its length, and we classify these algorithms by the ratio between the target vector V and the Gaussian heuristic of the lattice L. And if the ratio is between 0.95 and 1.05, we should use the lattice Sievin algorithm to solve exact SVP. And for the larger factor, the problem is called approximate SVP, and we should use lattice reduction algorithm, for example, BKZ or LLL. And if the ratio is smaller, especially smaller than 0.5, and this problem is unique SVP, we can use BKZ and combine with the sieve, lattice sieve to solve this problem. But all these problems are defined under the Euclidean norm. So sometimes we should use other norms, lattice hard problems under non-Euclidean norm to define a certain lattice hard problem. For example, signature forgery in DILISM. And in the document of DILISM, the designers claim that the signature forgery can be done by solving such equation, which is called the M-ISIS problem. And the solution Z and U are bounded by its infinity norm instead of the Euclidean norm. So the main differences between this M-ISIS problem and the problems we discussed above, there are two main differences. First is that this problem considers the infinity norm instead of the Euclidean norm. And secondly, in this problem, since there is a target vector T, it can only be turned into an approximate CVP, closest vector problem, instead of an approximate SVP. Approximate CVP can use candency bending to turn into approximate SVP, but the candency bending cannot always success, which we shall show it later. So how this problem relates with the existing lattice algorithms, and we shall discuss it below. First, the approximate SVP problem under the infinity norm. If we wish to solve it using an approximate SVP solver under the Euclidean norm, we should find the vector both short in Euclidean norm and in its infinity norm. So not every short vector in Euclidean norm is short enough in the infinity norm, so it has a success probability. And for solving approximate CVP or ISIS, we can use candency embedding to turn into approximate SVP or CIS. But this also success with a certain probability. It cannot always success. And the things in common is that not every short vector in the lattice is a required solution. So we summarize this to get a new lattice hard problem. We call it restricted SVP, which is the title of this paper. So we give a formal definition for restricted SVP. We define it by a predicate R, which we called it as the restriction. And R is related to a probability function. We write it as P-len. P-len means that a lattice vector which length in Euclidean norm is shorter than len. The probability for such lattice vector can pass the restriction. So we also add an additional we also require an additional property for the function p is that if the value of len becomes shorter, then the probability becomes larger. So finding shorter vectors in the lattice can lead to a larger success probability for solving the RSVP problem. So given the related probability function p, we can determine the size of the set of lattice short vectors such that there exists at least one vector in the set which passes the restriction with high probability. And this leads to the trivial algorithm for solving restricted SVP, which is a two-step algorithm. First, we run enough PQZ to reduce the lattice spaces. Then we run a kappa-dimensional sieve to output a set of vectors S. Next, we do exhaustive search on the vectors in S to find at least one vector which could pass the restriction. However, for a fixed value of kappa, which means that the fixed time cost for the sieving algorithm, the set of the output vector size and the length of the output vector are all also fixed. So the set may be too large or too small compared with the length of the short vector. So if the size is too large, we cost unnecessary extra time in finding the required vector. But if the size is too small, the success rate in finding the required vector is also small. So if we fix the dimension kappa, which means that we fix the length of the output vector, the output length of the output set of vectors. So how we could output a set of flexible size to avoid the two problems. And this is the main problem we wish to solve in this work. So the first approach, we called it flexible dimensional sieve, dimensional free. So if we run a sieve without a dimensional free, we output a vector set of size which is square root 4/3 to the kappa. And if we run the series full dimensional free, we output only one vector. So what if we use more flexible value for dimensional free? We choose f prime between 0 and f, and for this we can we suppose that we can output a set of size between 1 and this value. So we can output a flexible size which is smaller than the sieving size, the sieving without dimensional free. And we have such a theorem which claims that the output contains gamma to the kappa vectors, and gamma is defined as defined in the algorithm. Also, the length of the output vectors is also defined in this algorithm. And this is the correctness proof for the flexible dimensional free algorithm. But since we do not have enough time, we simply skip the proof. Next, if we wish to output a larger set, we could use the sieve then slice algorithm. Since the sieving set is a subset of the sub-lattice from dimension 0 to kappa. And if we wish to output a larger set, we should find more short vectors which in the lattice L, but not in the sublattice. So to find such vectors, we can first find non-zero short vectors in the projected sublattice from kappa to the dimension d. Then we find the closed lattice vector of T in the four-dimensional lattice L. Then V is a shortest vector in L, but not in the sublattice. So we can use randomized slicer to solve CVP given LCU. So we first run the sieving algorithm on the sublattice to get LCU. Then we use randomized slicer to generate more vectors given for input, we give the size of the output vector, and this algorithm can output a vector of the size s. So given the size, we can also bound the length of the output vector by the value represented by this formula. So we skip the correctness proof of this algorithm. Combine the two algorithms, we get a heuristic algorithm for solving restricted SVP. And the idea is simple. We select one out of the two algorithms according to the probability function P. But there is more problems remain to solve. Since in this RSP solver, the target root limit factor of the lattice spaces and the final sieving dimension are all considered as an input parameter of this algorithm. So, but in order to optimize the time cost of this algorithm, we should optimize the two values. This can be done by giving a complexity estimation for RSP solver. Then we can simply do exhaustive search on the two values of delta and kappa to minimize the time complexity of the RSVP solving algorithm. The time complexity estimation of the restricted SVP is not too hard, since it can be get by the PQZ time cost and the sieving time cost and the slicer time cost if we use sieve dense slice. For the first two, there are already many results in the literature. But for the slicer time cost, we make the following heuristic assumption is that the time cost for each output vector between the sieving algorithm and the slicer algorithm, since they both cost one visit to the NS data structure, we assume that the time costs are similar for the two algorithms. And this is our experiment, the experiment data, which show that the two time costs are actually close. Next, we proceed to the applications to the restricted SVP algorithm. So first, we use restricted SVP to solve approximate SVP under the infinity norm. So under this case, the restriction function is that the target vector has its infinity norm lower than a certain bound B. First, we verify the heuristic assumption in the document of DISM, which claims that the uniform distribution on a ball is close to a Gaussian distribution. So we give a formal proof for the assumption, and this leads to the theorem below, which claims that the related probability function can be expressed by the cumulative distribution function of the standard Gaussian. And although this is also only an approximation, we find that the two are extremely close by our experimental results. Next, we use RSVP to solve approximate CVP. Since approximate CVP can be turned into approximate SVP by the Canon's embedding like this, given a certain embedding parameter M. And SVP on this lattice can output a vector which its last element is C times M. And this vector corresponds with a correct solution to CVP only when C equals 1 or minus 1. And for other cases, for example, C equals 0 or C equals 2, 3, or other values, and the Canon's embedding fails to find the solution for CVP. And we give a theorem to show that there exists a choice of M such that the success rate is around 34.3%. And for small lattice dimensions, our experiment shows that the success rate is in fact larger. Next, we combine the two to get a security estimation for DSM forgery, since this can be solved by infinite norm CVP problem, and we use the Canon's embedding to turn into SVP. First, we consider the conservative estimation, and we use a single bound for the solution, the two solution vectors U and Z, and the related probability function is like this. We can express it by the formula like this, and we only need to determine M, and it can be generated using geometric series assumption. But if we consider different bounds for U and Z, we can remove the conservativeness in the DSM estimation, since for the conservative one, we consider the larger bound between BU and BZ, but for the non-conservative estimation, we consider the different bound or the exact bound for both U and Z. So to solve this problem, we can use the rescaling technique, which is also used in solving LWE, to turn the two bounds into a same bound. And the optimal rescaling factor is in fact BZ over BU, which means that the rescaling factor can turn the two bounds into a same bound. Yes. So this removes the conservativeness of the DSM estimation. And next, we give the estimation result for forgery in DSM, which is we minimize the value of the logarithm of time cost over success rate, and we use the gate count model and PQC estimation in the existing works. We give two estimations. First is the conservative estimation, and second is the non-conservative estimation. For the conservative estimation, we give the gate count estimation. We can see that the gate count estimation fits well with the core SVP estimation, considering the differences between core SVP and gate count. But for non-conservative estimation, we can get a higher and more accurate estimation for the DSM forgery. For the conclusion of this paper, the main contribution of this work, we first defined a new lattice hard problem called restricted SVP, and we gave heuristic algorithm for solving restricted SVP. Then we use restricted SVP to estimate the hardness of the ISIS problem under infinity norm. This can be turned into the first gate count estimation for DSM against signature forgery. For our future works, we can consider lower bounds for the hardness of restricted SVP, or consider more applications for restricted SVP. Furthermore, we try to find algorithms for restricted USVP or restricted LWE. And this is the final of this talk. Thanks for your attention. And since we are not able to attend the conference in person, so if you have any questions, so please contact me by my email, and my email is written here. So thanks again. Thank you.
We won't take any questions, but you can ask the author question by email. And now we switch to the coffee break.